and I'm going to take us to different AI algorithms, local search algorithms. One of them is hill climbing, which is a local search algorithm that continuously moves towards the direction of the increasing value to find the peak of the mountain or the best solution of the problem. Take an example whereby the agent is having more than 2 hills, but they're all not of the same height, so it keeps on moving towards the highest peak as shown in this image. It has a global maximum, the local minimum, and the current state. So the current state is where the agent is, the global maximum is where it's moving towards, then the local maximum, that's where it has checked, and the other side is increasing, so it takes the other side of the global maximum. Then another example of a local search algorithm is simulated annealing. This is a modified, it's a modification of hill climbing, whereby this one uses shaking in a way that the agent keeps on shaking until it finds the intensity of the shaking until it rests at the local minima. So simulated annealing is a modified version of hill climbing. It's suitable for nonlinear objective functions where other local search algorithms have failed, and it's a solution to start. A solution is to start by shaking hard and gradually, like let's say in this image, the agent starts from the starting point and then it descends to the local minima, but then the local minima is not the goal, so it has to shake and bypass the barrier to local search, then it lands in the global minima, which is the goal. So another algorithm is a genetic algorithm, which is a search technique used in computing to find true or approximate solution to optimization and search problems. This one uses processes like inheritance, selection, crossover, and mutation to evolve solutions over generations. It keeps on mutating for the better of the algorithm. This is used most especially in complex problems with large search spaces. It's normally used whereby you have complex search space whereby there are very many things that the algorithm has to do, like it has to go through a lot of data. Then the next one is this shows how to improve the usability of this algorithm using responsible and explainable AI. Responsible AI is where the model is able to think on its own, and it's responsible for its action, so it has to be keen. Then explainable AI is whereby everything that is done by the model is explained through the output. The output is explained like it can easily be understood. So how to improve the usability of these algorithms through responsible and explainable AI? So for responsible AI, it reduces bias, and also the ethical constraints are met, then fairness and inclusivity. Then for explainable AI, transparency in decision making is achieved. The traceability in evolutionary process is also achieved, and also interactive explanation, like I had said earlier. Someone is able to interact with a model, with a agent very easily. The next search algorithm is adversarial search, and adversarial search is a problem-solving technique that focuses on making decisions in competitive scenarios, whereby this is usually used in games. It is like they say, it is employed to find optimal strategies when multiple agents, often referred as players, have opposing or conflicting objectives. Then the next algorithm is the minimax algorithm. This is a recursive or backtracking algorithm which is used in decision making and game theory. It's also used in game theory. It provides an optimal move for the player, assuming that the opponent is also playing optimally. So in games like chess, the agent has to know that the player is going to make a certain move, so it has to make an optimal move, assuming that the opponent is also playing optimally. That's the minimax algorithm. And this is the function for the minimax algorithm. Then maximizer, there's a minimizer, maximizer, terminal mode, terminal values, all these. Then we have adversarial machine learning. Adversarial machine learning is a subfield that delves into the vulnerabilities of machine learning models, particularly their susceptibility to intentional manipulation. Adversarial machine learning focuses on crafting inputs that are designed to deceive models into making incorrect predictions or classifications. So this one deals with it's more like a testing kind of thing, by making the model make errors to test. So these adversarial examples exploit the weaknesses in machine learning models by introducing subtle modifications to input data, modifications that are often not noticeable to humans but significantly affect the model's performance. So that's what adversarial machine learning is all about. It's about making the model, driving a model into making a mistake, or tricking the model. So that's adversarial machine learning. Types of adversarial attacks could be evasion attack, poisoning attack, privacy attack, and backdoor attack. So it's applied in autonomous, healthcare, finance, and cybersecurity, because those are sensitive areas that one has to be sure about the model's performance, the model's working. The defenses and mitigation strategies, one of them is adversarial training, defensive distillation, randomized smoothing, certified defense. All those are defenses and mitigation strategies in adversarial machine learning. So from this image, so it summarizes most of the other attacks. Model poisoning, for example, model poisoning attacks the availability of the model, whereby it affects the model control by then lead to the unavailability of the model. Then we have clean label poisoning. This attacks the label limit, thus affecting the availability of the model. Then we have data poisoning, which attacks the training data control, and thus the availability is attacked. Then there's also energy latency, and this attacks query access, thus the model is unavailable. Then we have those that attack the integrity. One of them is model poisoning. This attacks the model control. Another one is clean label poisoning and clean label backdoor. They attack the label limit. We have evasion and backdoor poisoning. They attack test data control. Backdoor poisoning, on the other hand, attacks source code control and training data control together with targeted poisoning to attack the integrity of the model. We also have black box invasion, which attacks the query access, thus the integrity is attacked. Then we also have things that attack the privacy of the model. We have model extraction, which attacks the query access, thus the model is attacked. Then when the model is attacked, there is no privacy. We recall there's also reconstruction, membership inference, and property inference. These also attack the query access, and then the data. Once you have the query access, you have the database. Thus, no privacy at all. Well, the adversarial search and adversarial machine learning are related in a way that the adversarial machine learning adds that function to bring in the error, thus confuse the metric in order to test and be sure of the integrity, of the availability, and of the privacy of the model. And it says that adversarial machine learning and adversarial search both involve a strategic competition between two entities, one attempting to deceive or attack, the other attempting to defend or optimize, same as two players in adversarial search. They both have competitive dynamics, they both have minimax strategy, and they both have exploitations and weaknesses, just like any other model. Optimization in competitive environment, they also have that feature. They all have continuous loops. And this comes to the end of my presentation. Thank you so much.